Hi gang, Mass 6610 effect sizes. Sorry for the abrupt ending in the previous video. I had a technical glitch with R, and it just froze up and did some wacky stuff, so I don't really know why. Um, but in terms of the instruction, it's not really going to matter. All right, effect sizes take on kind of an interesting dilemma here. I'm going to show you one, demonstrate one to you. Um, and I'm going to tell you that we're not going to use that one because of certain reasons. Uh, so the first effect size I want you to think about is actually leading up to something called eta squared. Eta squared is just kind of a squiggly looking in. Um, and it turns out that eta squared is really easy to find. Eta squared is just going to be the sum of squares between over the sum of squares total. So in our case, I've started over with R because it did some ugly stuff. Let me create this. So values independent data equal data, kind of redundant, right? So this set of square would be the sum of squares between, which would be 626.7 divided by 626.7 plus 893.8. So eta squared would be 0.4122. Now, to change this into what we need is the effect size R, because for R we have this standard of 0.1 to 0.3 to 0.5, where this is a small effect, and this represents a medium effect, and of course this represents a large effect. So we can calculate R by taking the square root of 0.4122, which so 0.642. So according to this standard, that's clearly above 0.5. So let me move that over. We see that effect size represents a large effect. So something going on here between analyzing quiz scores, the difference in mean quiz scores across instructor, professor. Now, there's a way that we can also take a look at this using the uh, LSR um, package. I believe it's LSR. Yeah, okay. Using the LSR, and it's just the eta squared command. And you can see that we get the same thing. What I would want you to focus on is the eta squared part. So that's the partial eta squared. Um, and you can see that this value aligns with what we got previously, off a little bit due to rounding. Now, drum roll, please. I don't want you to use this. This is just one effect size, but that we report, and we see reported a lot. This turns out to be very biased, or at least partially biased, somewhat biased, because this calculation is made on the sum of squares calculation, which comes directly from our sample data, right? And there's no adjustment that's been made to accommodate for the fact that we want to represent the effect size for the population. So for that reason, this process turns out to be, slightly biased, and we will not use it. So what I do want you to use, however, it's got an interesting feature because it helps us and calculating our power is omega squared. And omega squared just kind of looks like a W squared. And the formula for this is not too bad. We take the sum of squares between minus the degrees of freedom between times the mean square within, all divided by the sum of squares total plus the mean squares. I always forget if this is between within. So for us, this again, we have our model. Let's just go ahead and get the sum of squares total. So we're going to take 626.7 and add 893.8. All right. So sum of squares between would be 626.7 minus degrees of freedom between would be 2 times our mean square within is 37.24. And I want that to be divided by the sum of squares total plus 37.24. All right, so we get 0.355. And the scale for this actually turns out to be, again, this is, I forget, I think it's 0.01, 0.05, and then 0.14. So this is small, medium, and large effects. So the 0.355 clearly is bigger than 0.14. So we have, again, represented a large effect. Now, there's another package called, let's access it, it's just called effect size. Kind of convenient, right? And we can run effect size for our model, and we can do type equal to omega. So it returns the omega squared, again, giving us 0.35. It also includes the 95% confidence interval, which is very, very handy. Okay, so we're clearly observing a represented large effect. Now, the reason this, and I would want you to report the omega squared. Now, the reason this is nice is because if we go to calculate the power, one thing we should know by now is that when conducting ANOVA, we are residing in the F distribution, so we use the F test. And we're going to choose the ANOVA fixed effect omnibus one way. Now we have our effect size, but notice the effect size is the effect size F, and we didn't calculate that. We calculated the omega squared and the eta squared. So more about that one in just a second. But I know I want my type 1 error rate to be 0.05, which is set at. I want the power to be 0.8. And we have 3 groups. Now, if I open this drawer over here and choose effect size from variance and then come down and do a direct calculation, I can do my partial eta squared. So the partial eta squared was, what did we find out for that one? Did it earlier, right? Yeah, partial eta squared was 0.4122. So the reason we need both of these, I don't think I've really explained this or described this appropriately. We use the eta squared in G power. So I didn't completely waste your time up here, even though this is, in my opinion, at least it's a biased result. But when reporting the effect size for the ANOVA, I want you to report the omega squared. And really, there's not a lot too cool here. The cool part's going to get when we dive into the multiple comparisons and we actually get effect sizes for the multiple comparisons, which I'll do in the next video. All right, so let's calculate. So 0.83, let's transfer to the main window, and then let's close this drawer. And it looks like everything is set correctly, so we calculate. So our total sample size that we would need would be 18 to get a power of 0.83, right? And so we have adequate power with the sample size, I think, of, I forget, I think there were 9 in each professor, so I think we have a sample size of 27. We can actually run into doing omnibus, but do a post hoc and see the power that we actually achieved. So our sample size was, again, I think 27. Let me double check that. I'm pretty sure that, yeah, 27. So type 1 error rate 0.05. We have our effect size, so 27. So we're going to get power actually above 0.8. So we get a 0.96 power. So the probability of rejecting a false null is 0.96. It's going to happen almost every single time. So gang, that's about all I got on effect size and using G power to calculate priori and a post hoc analysis. All right, take care.